record to the cloud.
Yeah.
Are we?
Thank you.
All right.
Okay. So yeah, thanks for this great seminar, which I think is going to be a lot of fun. People should like look up the speakers. I'm planning on coming and eating lunch here regularly. This is joint work with a bunch of great people, many of whom are in the room. Osbert's over there. Darwin is proving something for the ITCS deadline tomorrow. Chris graduated over the summer and is at Stanford now. George is spending the semester at Simons, and Ramya is over there. So we've got, especially over the last 15 years or so, really good at making point predictions. We've got machine learning algorithms that you can feed tons of data and can try to, on new examples, predict what their label is going to be, and oftentimes they're right. But they're not always right in a case. And especially when we are going to try to make consequential decisions as a function of the predictions of these algorithms, we'd like to have some way of knowing when they're going to make their mistakes. Like, what are the examples we feel confident in their predictions, and what are the ones we should not? And so we need a way of quantifying uncertainty. We need a language for talking about the uncertainty of an arbitrary model, if it's a complicated one. And one very simple way, but one that has sort of nice interpretable semantics, is by giving prediction sets. So rather than giving the point prediction, like, this thing is a fox squirrel, we might give a set of predictions. For example, maybe we're pretty sure that this thing is a fox squirrel, so we just say fox squirrel, but maybe we don't know if this one's a fox squirrel or a gray fox, and we don't know if you're talking about this thing or this thing, so maybe, bucket is what you were looking for. Or maybe we give a set of predictions, okay, like marmot or fox squirrel, but we're pretty sure it's not a car. And the semantics of this prediction set, okay, should be that with some target confidence level, say 95%, we are asserting that the true label is in the prediction set 95% of the time. Okay, so it's a way of specifying how uncertain we are, not just the degree of uncertainty. The more uncertain we are, maybe the bigger the prediction set, but actually specifying where our uncertainty is. Okay, so this is for like a classification problem. For a regression problem, a prediction set is potentially just an interval, something you're maybe familiar with if you've studied statistics, like a prediction interval for a linear regression problem. Okay, so our goal is to endow black box predictors with prediction sets, and they should contain the true label, say, with 95% probability. Okay, so let me tell you about a very simple standard way of doing this called conformal prediction. If you haven't heard about conformal prediction before, you can ignore the rest of the talk. Cute idea here that is worth remembering. And it's an extremely simple method for fixing arbitrary black box models with prediction sets that have some semantics. I'll complain in a moment about the semantics, but let me tell you what the method is. So first, we start with an arbitrary model for making point predictions. So for example, having a running example of a simple regression problem, I might have a regression model that takes as input the vector of features and just output the point prediction like a number. On top of that, I will have a non-conformity score that, given an example X and a proposed label Y hat, tells me how much, so essentially smaller values of the non-conformity score tell me that the label conforms to the prediction of the model better. So in the spirit of walking through the very simplest example, if I've got a regression problem, the very simplest non-conformity score you could imagine, it's just the absolute value difference between the prediction of the model and the proposed label. Labels that are farther away from the prediction of the model, we say conform less well. Okay, so this is the prediction of the model. My non-conformity score would be the distance between the label and the prediction. Okay, and like in what's called split conformal prediction, you just take a holdout set, you take some data sampled from the same distribution you hope to deploy your model on, and then you just find the smallest threshold tau, such that 95% of the labeled examples have non-conformity score that is less than tau. Okay, you just find like the 95th percentile, like quantile of the non-conformity score distribution on this holdout set. And then on new examples, you just use the following prediction set. Okay, a new example X comes in. I know what my model predicts, f of X. I know that on this holdout set, 95% of examples from this distribution have non-conformity score less than tau. So I just predict the prediction set, which in this case is just an interval around my prediction of with tau of the set of all labels that have non-conformity score less than tau. Okay. And it's like immediate, if you just think about this for a minute, that if all of the data points are sampled IID from the same distribution, that the probability that the label on a new example is covered by this prediction set is at least 95%. Okay. Because the data from the holdout set was exchangeable with the new data, and we picked the 95th percentile of this distribution. And this is a marginal guarantee. I'm going to talk about that and sort of zoom in on what that means. But basically, it means the probability in this statement is over everything. It's over the randomness of X, Y, the holdout set, everything. Okay. And this was sort of like the very simplest example, but in general, if you have any model and any non-conformity score, you can define a prediction set like this. It doesn't have to be a regression problem, it could be a classification problem, and this guarantee holds immediately. Okay. This is sort of the very basics of like split conformal prediction. But before I go on, other questions about this? Okay, so remember it gives marginal guarantee. Let me now beat up for a little bit on marginal guarantee. So suppose we are in the position of making some consequential decision. So maybe there's a pandemic going on, people are coming into the hospital, and I need to marshal scarce resources. Maybe I'm trying to predict what this patient's blood oxygen level is going to be tomorrow, so I can decide whether they need to be admitted to the ER or not. And maybe I've trained a machine learning model on this, right? So I've got some model, and it says, look, given your features X, everything I have, as part of your medical record, our model predicts that your blood oxygen level in 24 hours is going to be something after that. And since we're going to decide whether to admit you to the ER or not, both the patient and the doctor might be interested in the question, how sure are you of this? And so if the doctor has, read a conformal prediction paper or the talk up until this point, they can say, well, hey, I've got a 95% prediction interval that your blood oxygen level is going to be between L of X and U of X. And maybe they're going to make some decision if this interval is in the dangerous region and, or if it overlaps the dangerous region. And our patient and maybe the doctor, if she's curious, thinks, what does this really mean? What are the semantics of this for me? And so ideally, right, if you're the patient or the doctor who cares about the patient, what you would sort of wish that this guarantee meant was that there was a 95% chance that the patient's label was going to fall into this interval conditional on everything you knew about them, conditional on everything in their medical record, anything you think was medically relevant. And if we're conditioning on everything, you might sort of ask, well, what is the randomness taken over in this probability statement? And it would somehow have to be like the unrealized or unmeasured randomness of the world, conditional on everything we've seen before. If we've got a large feature space, it's probably not an average over patients that we've seen that are identical to this patient, because we probably haven't seen anyone who's identical. But if this were the semantics of the prediction interval, then the patient could reasonably use this probability as a way to guide their decisions, because it would be speaking to them as an individual. Okay, but that is not what the promise of conformal prediction. The promise of conformal prediction is that this coverage is marginal. Okay, the guarantee is this. And this looks a little bit like this, but there's an important difference, which is that here, the probability is not just over Y conditional on X, it is over X as well. This statement down here is really an average over patients. It says not there's a 95% chance that your blood oxygen level falls within the interval. It says for 95% of people for whom we make predictions, our predictions contain the true label. But maybe not for you, right? We're averaging over a large and heterogeneous population. Right, so let's go back to our doctor. If he says, I've got a 95% marginal prediction interval that your blood oxygen level will be between L of X and U of X. And our patient might, for example, worry, well, I'm part of some demographic group that represents less than 5% of the population, say, so entirely consistent with the promise of the marginal prediction interval, which might be correct, might be the event that it's always wrong for this patient. Not just always wrong for this patient, but always wrong for people like this patient. Maybe this 5% of the population is actually a medically relevant demographic group that this model we've trained has just failed to pick up on. And it never covers the label in this population. It covers the label more than 95% on everyone else. And the marginal prediction interval has just papered over this discrepancy. Okay, so this is a problem with marginal prediction intervals. Now, of course, there's an easy fix if the groups are disjoint. We can just, there's only 5 kinds of patients, and every patient is one of those 5 types. We could just separately do this for each of the groups. That works. But groups are often not disjoint. So here we are. Our patient asks, "What about for people like me?" The doctor thinks, what does that mean? People like me. And so maybe she says, well, for African Americans under the age of 50, the 95% prediction interval is from A to B. And for women with a family history of diabetes, the 95% prediction interval is from C to D. And for people with egg allergies and no history of smoking, the 95% prediction interval is from E to F. And these groups are not mutually exclusive, right? Our patient might be simultaneously a member of each of these groups. And remember, right, a marginal prediction interval is just an average over a large set. So entirely consistent with the definition of a 95% prediction interval is the possibility that A to B might be disjoint from E to F. And so it is not at all clear what our patient is to do with this information. Coming up with marginal prediction intervals for different groups that this patient is a member of is not very useful for the patient because the predictions might be entirely different. Okay. This is sort of complaining about marginal prediction, then we're going to try to do something about it. But is the complaining part clear? Okay. So what does this mean? Oh, let me complain about one more thing. So the standard assumption in conformal prediction is that we've got data that is drawn IID from some distribution, or maybe it's not IID, but at least it's exchangeable, which means that I can permute the data and not change the joint probability of the data. And roughly speaking, that means we're assuming that the future must look like the past. Now that's an awfully convenient assumption that's made in a lot of machine learning, but it's often not true, right? Like in our pandemic example, it might be that as the pandemic progresses, the demographics of who it's affecting change over time. Maybe it's initially wealthy travelers coming back from Europe, and it's essential workers, right? So that's a sort of covariate shift. Maybe as treatments improve, the relationship between the features and the labels changes, right? That's sometimes called concept driven. Right? The distribution can change for all sorts of reasons in unanticipated ways. Okay, here's a cartoon whose punchline is that if I look at the distribution over your Christmas wishes, over the course of your life, these are not drawn from an exchangeable distribution. Lightning the joke. Has everyone paused to appreciate the cartoon? Okay. So our goal is to mitigate both of these problems. We want to make stronger than marginal guarantees. I'll tell you exactly what we're going to promise. And we want to assume nothing about the data. We want to assume that make no assumptions that the data is drawn from some distribution, or that, the distribution shifts in some well-defined way. We want to assume nothing and work in a fully adversarial model. Okay, so let's talk now about how we might offer something stronger than marginal guarantees. Let me start by talking about calibration, which is kind of a warm-up, and then I'll say what we offer. So let's think about the problem of testing a weather forecaster, seeing if they know anything about what they're talking about. Right, you turn on the TV every day, there's this guy, and he says, hey, there's a 20% chance of rain tomorrow. There's a 60% chance of rain tomorrow. How can we tell if he's right or not? Right, tomorrow only happens once. Well, maybe that's too hard, telling if he's right or not. Maybe we just want to see if he passes some simple statistical tests that he would pass if he knew what he was talking about, and would sometimes catch him out if he was doing something too naive. So the very simplest statistical test maybe we could ask is we could say, okay, well, I'll just average up over all of the days of the probability that this guy is predicting rain. And then I'll just figure out by averaging over all of the days how often it rains, what is the baseline rate of rain, and make sure those things are the same. Okay, that's something that, he would, the oracular weather forecaster who really knew what he was talking about would pass, but that's too easy to pass, right? Like I could always predict what happened yesterday to pass that test. If it rained yesterday, I could predict 100% chance of rain today. If it didn't rain yesterday, I would predict a 0% chance of rain today. I would, on average, predict on average, I'd be correct, but like, obviously, I don't know, obviously, I do not look like the oracular weather forecaster. So checking that the forecasts are calibrated is just a slight strengthening of this statistical test. Okay, let me zoom in on the subset of days for which you predicted a 20% chance of rain. I'm going to check on that subset of days that it rained 20% of the time. I'm going to zoom in on the subset of days for which you predicted a 30% chance of rain. I'm going to check that on that subset of the days it rained 30% of the time. Okay, the oracular weather forecaster would satisfy this test, and now it's maybe a little bit less hard to pass this test if you don't know what you're doing, although still possible. Okay, so that's calibration. Maybe some of you have heard of calibration before, but let's just, as a refresher, does everyone now understand what it means for a forecaster to be calibrated? Okay. Don't look at this box yet. Let's look at these pictures. Here's another way I can ask for sort of a stronger than marginal. So calibration is a stronger than marginal guarantee in that it's not averaging over everything. It is conditioning on the prediction of the forecast. Conditioning on the prediction. Okay, so it's now a stronger than marginal guarantee. I now want to ask for something that's stronger than a marginal guarantee in another way as well. Suppose there's groups that intersect. So maybe they're defined by shape, triangle, circle, square, star, but they're also defined by color, blue, green, orange, and they're defined by whether you're glowing or not. Okay, so you can be a member of multiple of these groups. I might want predictions that are correct, even when I zoom in on one of these groups. So maybe I'm giving prediction sets, and I want them to cover their label 95% of the time overall. But also I want to be able to zoom in on the squares. And when I just look at the sequence of examples consisting of squares, it should cover 95% of the square labels. I should be able to zoom in on the circles and the triangles. But also I should be able to zoom in on the red examples, which should cover 95% of their labels. Also, I should be able to zoom in on the glowing example, which should cover 95% of their labels. Right, so I want the correct coverage when I zoom in on these different groups, even though these groups intersect. Okay. And then finally, what we're going to promise, which we sort of call threshold calibrated multi-valid coverage, is simultaneously asking that you can condition on, zoom in on any one of these groups, and that you can condition on the prediction of the model, on the threshold produced by the model, right? So it should be correct on these groups, not just marginally, but also calibrated. Okay, so we'll say that a sequence of 95% prediction sets, which are now, I would have a question.
Yeah, does this also have any promises that it wants our intersections, but something that's slowly as a whole?
If you wanted, so you'll, there's going to be some collection of groups that we offer promises on that we assume nothing about. So if you care about the intersections, add them.
You got the
That's right. If you so I'll say out loud what the guarantee is, but we have this set of groups on which we're going to make promises. That can be anything. We'll have some dependence on how many of them there are, but they can be anything. We do not automatically make promises on the intersection of those groups, but because we assume nothing about the structure of these groups, if you care about the intersection of those groups, you can throw those into the set. Okay. So first, so just recalling conformal prediction. A prediction set given a nonconformity score is defined now just by a single threshold. We're going to predict the set of all labels whose nonconformity score on this example is less than the threshold. Okay. So when we make predictions, that corresponds to every day predicting some threshold. Okay, basically we're trying to predict like a quantile of the nonconformity score distribution. And we'll say that our sequence of prediction sets is threshold calibrated and multi-valid on a sequence of examples with respect to some arbitrary, possibly intersecting collection of groups G, if for every single one of the groups in our collection, and for every single threshold that our algorithm might predict, if we condition on both the group and the threshold we predicted, meaning we zoom in on the subsequence of examples corresponding to that group for which our predictor predicted a particular threshold, even then we want 95% coverage. And so it's stronger than marginal coverage in two ways. We can condition on group membership, and we can condition on the threshold we calibrated and the group condition. Okay. The promise makes sense. Okay. Let me just sort of point out that, so like, you know, I gave you this like one slide at the beginning talking about split conformal prediction. I gave this one example of like the simplest possible nonconformity score for like a regression function, the difference between the prediction and the label. Although split conformal prediction itself is very simple, there's like a, you know, now a cottage industry basically of people writing conformal prediction papers where the main contribution is clever new nonconformity score. Okay, so there's all sorts of stuff you can do beyond that simple nonconformity score. For example, since really what I'm trying to do is predict quantiles of something, so I somehow quantile of the label distribution, say, instead of training like a regular regression algorithm, I could train like a quantile regression algorithm. And it's trying already to predict, you know, like quantiles of the label distribution, which means that if it's doing a good job on some examples, it might give much narrower intervals than others. Quantile regression isn't guaranteed to succeed, but we can take the distance between the label and the boundary of the prediction interval induced by quantile regression as our nonconformity score and just expand these intervals or contract them until they're correct. Okay, that's some way of giving prediction intervals that are responsive to covariance. You know, you can derive for classification problem nonconformity scores from the softmax output of a neural network. So we don't have to be talking about one-dimensional intervals. We can be talking about, you know, prediction intervals that say this is either a Chihuahua or a blue-brain muffin. I don't know which one. Okay. The point is that this whole cottage industry of designing nonconformity scores is complementary. Like we are going to give like a wrapper method that is going to be like a replacement for split conformal prediction, but is just as general. It can take as input any nonconformity score. And so if you like this one, or if you like this one, think about that, you know, instantiating our method with that nonconformity. It's agnostic to what the nonconformity score is. Okay. So the beauty of these nonconformity scores is that they make the problem one-dimensional. Right? Once we fix a nonconformity score, the conformal prediction sets are parameterized just by this threshold, which means we can think of the problem as just predicting, as just giving prediction intervals that have their left endpoint at 0 and have their right endpoint at some threshold we need to choose, so that these one-dimensional prediction intervals cover the nonconformity score of the distributions we're interested in 95% of the time, right? So we don't care what the nonconformity score is, whatever it is, reduces the problem to some one-dimensional prediction interval problem. Okay, so you know, we see an example. It's nonconformity scores here. This is the threshold we picked. We cover the example. This threshold we picked with the nonconformity scores here. We did not cover the example. So from now on, I'm just going to think about not real valued nonconformity scores and prediction interval, one-dimensional prediction intervals that cover them or do not. But remember, this captures the full generality of conformal prediction. The nonconformity scores are induced by the distribution on these one-dimensional scores is induced by your favorite choice of a nonconformity score function.
All right, you need some assumptions on the function?
No.
I think I missed one thing. When you have multiple classes, you're gonna have a single conformity score that covers all the different classes. So when you talk about this intersectionality here.
Yes, so the nonconformity score could be anything. It could be, let's just think about the very simplest example. We've got a regression function, and our nonconformity score is just the absolute value difference between f of x and y. Okay, that's it. Now,
I'm concerned with the whole point you're going to is multiple intersecting classes or non-intersecting classes possibly.
that's right.
And so there's a single score which captures.
The nonconformity score can be anything. Our sort of guarantees hold for any nonconformity score. The role of the nonconformity score is to reduce these sort of what might be complicated labeled examples, like a picture of a chihuahua and like, 1 of 1,000 like labels to like a number. S of, the pixels, comma, chihuahua gives us like a number now. And now, right, the problem, like once we've got this one-dimensional problem, this multi-valid coverage guarantee, this means, okay, every day we're gonna see basically X and then a non-conformity score. Every day we have to pick a threshold tau. And our goal is if we zoom in on the subset of examples defined by any of the groups and any of the thresholds we pick, that we cover the non-conformity score 95% of the time, even on that subset.
I guess my concern is how did this scale with the number of subsets? I'm worried that this is almost multiplicative, and if you have enough subsets, then it becomes attractive.
We will, yeah, so
We'll get there, maybe.
we'll get there. Exactly. So there will, but to sort of give it away, our coverage rate will scale very mildly with the number of subsets, only logarithmic. But the running time will scale linearly with the number of subsets. So if there's really a lot of them, then you better buy a computer.
And then you want to make tau as small as possible.
Yeah, although the way we're gonna do that is we're gonna ask for like 95% coverage exactly. Like we're gonna be unhappy both with 94% coverage, but also with 96% coverage. So if it's like a continuous distribution, if you're systematically making tau too big, the result is you're gonna be overcovered. Good. Okay. Questions about that? So now let me give you the actual like setting we're working in. It's going to be like an online adversarial prediction setting. Here is the adversary. Okay, so this is a sequential prediction setting. Time will proceed in rounds. At every round, an adversary selects an example, XT. Okay, these are like the features. And maybe the adversary also has in mind the label, but doesn't show it to the learner. Okay, so the learner just sees the example. Then the learner has to choose a threshold. Okay, which, if we also have a nonconformity score in mind, translates into like a prediction set. Might say Chihuahua or blueberry muffin, but like from our perspective, since we've reduced everything to this prediction interval problem, they just have to choose a threshold. Okay, and then we output the prediction set. The prediction set we output today is just the set of all labels that have nonconformity score less than the threshold. And then only then does the adversary reveal the label, and we learn whether our prediction set covers the label. And after that happens, the learner gets to learn the label. Actually, the learner doesn't care what the label is. The learner really only cares what is the nonconformity score of the label, so they can learn if their threshold covered it or not. And that's it. Then we continue. And at the end of this interaction, we will have generated some transcript consisting of xt, yt, tau t for each of capital T days. And our goal is that the empirical distribution induced by this transcript should satisfy our multi-valid coverage guarantee. Okay, so there's no distribution here. The adversary can really do anything. The adversary can have the, myopic goal of just making sure that like our algorithm doesn't satisfy multi-valid coverage. The adversary could model some more natural kind of distribution shift, arbitrary covariance shift at different times, arbitrary concept shift. The point of an adversary is not necessarily that we believe that the world is adversarial, it's that we believe that we don't know everything about the world, and whatever it's doing, we would like to not have made assumptions that are not satisfied. So this is sort of like an assumption. This is like a model that has sort of minimal assumptions, and so we're very likely to not have violated our assumptions. Okay, so it's a challenging model. You are indeed allowed to use randomization.
And are you allowed to remember the realization, the random list that you put down
Yes, you can do whatever you want. And the adversary can also do things as a function of everything you've done in previous rounds. The only thing the adversary can't do is things that depend on your action. Okay, the model clear?
So you have to just exchange a bill of something. You require to do.
No, exchangeability doesn't even make sense without a distribution. There's no distribution at all. So this is sort of like the opposite of exchangeability. Like exchangeability is assuming the world is very nice, that there's a static distribution that points are basically drawn from. Here, things can change in arbitrary and unanticipated ways between every round. So no exchangeability or anything else. Make sense? Okay. Okay, so let's say a little bit about how we do it. The first thing is like, what is it we should be measuring? So, what is our goal? Right, so let's start like counting the right thing. The multi-validity asks that we can zoom in on a subset of the examples determined by a group they might be a member of and a threshold we might predict. So for a particular group S and a particular threshold tau, let's say that at round little t, n S tau is just the number of people we've seen who are a member of group S and for whom we predicted threshold tau. This is like the number of people in one of the groups that we're supposed to care about when we're promising multi-valid. Okay. Now, our goal was on each of these groups to get 95% coverage. Let's measure how far we are from that goal. Okay, let's say that VST is our coverage error on that group. It is the average over all of the people in that group that we've now zoomed in on of the empirical frequency of our coverage event, the frequency with which we actually predicted a threshold that covered the label, minus our target, 95%, the absolute value of that. So if we had like perfect coverage, if we had exactly 95% coverage on each of these subsets, these B quantities would be 0, all of them. And in general, like we sort of want, you know, like all of them to be kind of small. Okay. So let's think about actually like what is the best kind of thing we could hope. Like suppose the world was really well behaved, things were coming from a distribution. We knew what that distribution was, right? So we were truly predicting correct 95% prediction intervals as measured on the underlying distribution every day. What empirical coverage would we expect? Well, if I flip 100 coins, you know, I expect 50 heads, but that doesn't mean I'm going to get exactly 50 heads. I might get, you know, 42 heads. In general, because of like the law of large numbers, if I flip n coins, I sort of expect deviation from the mean that's on the order of 1 over root n. Okay, so that's what we're going to shoot for here as well. You really can't do better than that. Even if you knew everything, you'd get sort of empirical coverage error on some group of size n that sort of differed from the mean by something like 1 over root n. Our goal is that for each of these groups we care about, parameterized by, you know, a group S and a threshold tau, that our empirical coverage error should scale as like 1 over root NST, something like the variance you would expect on that group if you were predicting correctly every time. Or said another way, what we want is that for every group and for every tau, I would like that when I look at this V quantity, right, which remember would be 0 if my coverage was exactly 95%. Maybe it's too much to hope for that it's 0, but I want it to scale like 1 over root the number of people in that bucket. That would be what I would get if points really were coming from a distribution and I knew what that distribution was and I was predicting correctly every day. Okay, I want to get the same thing even though there's not a distribution. So the thing I want to do is I would like to make sure that the maximum over all of these quantities doesn't get too big, doesn't get more, you know, bigger than 1. Right? The maximum over all of these things is sort of like the thing I'd like to control. And it's kind of annoying to control though, right? Because it depends on the whole history, right? Like this is a function of the whole transcript so far. So I'm gonna like cross my fingers and hope that a greedy strategy is gonna do a little bit better. Or sorry, not gonna do, that a greedy strategy will be sufficient. Right, so the sort of philosophy of the algorithm will be, well, okay, like what's done is done. You know, I can't change the past. I've made predictions so far, like I have some coverage error. But like what I would like is that when I make today's prediction, that my loss after today's prediction should not have increased very much compared to my loss before today's prediction. Like the thing I can control today is the increase in that loss. And I would really like to design my algorithm so that this increase in loss can be bounded. And if I can do that, then just by telescoping, if the increase in loss every round is small, the cumulative loss at the end of time will also be small. That's going to be the premise. Okay. Okay. Interlude, zero-sum games. Many of you will have played rock, paper, scissors. This is a zero-sum game. In general, a zero-sum game is defined by two players, a minimization player and a maximization player. So in rock, paper, scissors, maybe we say the payoff is 1 if I win, and the payoff is 0 if you win. I would be the maximization player, I would like to win. You would be the minimization player, you would like me to lose. You'd like to minimize my payoff. We will identify the minimization player with the learner, who'd like to minimize this loss. And the maximization player with the adversary, who'd like to maximize it. And they, you know, in a zero-sum game, both of these players have some finite strategy, A1 and A2. And there's a utility function that says, what is the payoff the minimization player would like to minimize and the maximization player would like to maximize as a function of the action chosen by each of these players. Okay, so that's just some function mapping an action of the learner and an action of the adversary to a number. And this extends the distribution in the natural way, right? Like in rock, paper, scissors, I pretty quickly learned that I should probably randomize, even though it's tempting to play rock every round. And if I'm randomizing and you're randomizing, then my utility is just an expected utility when we draw an action from these distributions. And like the one fact you should know about zero-sum games, like the sort of defining fact, is von Neumann's min-max theorem, which says order of play doesn't matter. So I might think really hard about my rock, paper, scissors strategy. And I might tell it to you, which normally seems like a disadvantage, right? Like if you know my strategy, you have the freedom to like, you have the ability to like use that information and best respond, right? And I'll say, okay, here's my strategy. I'm gonna like randomize uniformly between rock and paper and scissors. And in rock, paper, scissors, that doesn't actually help. Like if I tell you my optimal strategy, you know, like we're going to do just as well. If you tell me your optimal strategy, we're going to do just as well. Von Neumann's min-max theorem says that's true in general for zero-sum games. That is, if the minimization player is forced to go first and announce their randomized strategy, and then the maximization player can exploit that information to best respond to maximize the payoff will actually be the same as if the roles were reversed and the maximization player got to go first. Or had to go first, had to reveal their strategy to the minimization player, and the minimization player got the best response. Okay, that's like the fundamental theorem of zero-sum. Okay, so let's define a game between the learner and the adversary. The learner's action set will be threshold. Okay, we'll have to appropriately discretize them. The adversary's action set will be nonconformity scores. The payoff will be this change in potential, right? The sort of increase in loss as a result of this round. The learner would like to make this small. The learner wants the increase in loss to be small. The adversary would like to make it large. Zero-sum game. Okay. The fundamental theorem of zero-sum games says that if we want to like reason about how well we can do in this game, order of play doesn't matter. So in reality, of course, the learner goes first. The learner has to commit to an actual algorithm, which is a strategy at every round. And we need theorems that hold for arbitrary adversaries, even adversaries that are tailored to the algorithm. Right? So in reality, learner goes first, then adversary does respond. But the min-max theorem says if we want to figure out how well the optimal algorithm can do, we can imagine the adversary goes first, announces his distribution, then the learner best responds. Now, if the adversary announces his distribution, the distribution on non-conformity scores, the learner's problem is exceedingly easy. All the learner does is read off the 95th percentile quantile from the CDF of the distribution that the adversary hopefully announced to it. Right, like giving prediction sets for a label distribution that you know because the adversary told it to you is very easy. Right, so long as the distribution is continuous, there is some threshold that gets 95% coverage. You just read it off.
I have a question.
Yes.
I'm confused about one thing. So that loss, shouldn't it depend on the entire history because it was based on some average, right?
So the loss is, this thing depends on the whole history. This thing is just the increase in loss as a function of the actions that I and the adversary play this round. So this, although I need to know the history to define this loss function, because I need to know the history to know what L t minus 1 is. This is a function that is, depends only on the threshold and the label. That's why it's important that we sort of zoom, that we sort of take this like greedy approach. Oh. Now, skipping over like a whole bunch of calculations and stuff and just giving you the intuition. When the adversary goes first, it's sort of very intuitive that you can do well. Right? Like it's making you the oracular classifier. You actually know the label distribution every round. So you can actually make these sort of otherwise impossible predictions that are actually conditionally valid, like predictions for this person in front of you today. Because the adversary has told you the label distribution for this person in front of you today. So you actually get 95% coverage, like for every single person in this world, this counterfactual world in which the adversary is telling you things. And so in particular, also multi-valid coverage. So intuitively, when the adversary goes first, it's like, they go through the calculations, but maybe you can believe at least that there's a way to play that guarantees that loss doesn't increase by very much. But then the minimax theorem says, well, okay, if that's the case, then there must exist an algorithm. So far, this is just a non-constructive argument. Doesn't tell you what the algorithm is. But there must exist an algorithm that allows the learner to do just as well against an arbitrary adversary. Okay, this is sort of the magic of the min-max theorem. Okay, so what's the algorithm? Well, there's like, you've got like no choice here. Like there's a crank. The algorithm is to play the equilibrium strategy of the game we've just defined. So you have to sit down and compute what that is. Yes.
Do you know what the worst case is? So it only helps you if you can characterize.
Do I know what the worst case is? What do you mean?
So to use this observation, you need to know what the worst case is.
So let's be clear about what we've shown so far. We've argued that the value of this game is, small, good for the learner. Meaning, if the adversary goes first, like the max min value is small. The min-max theorem has told us that therefore the min-max value is the learner goes first. But it hasn't, like there's nothing for us to like use yet. Like there's no algorithm yet. It's just telling us there exists an algorithm. And what is that algorithm? Well, the way to access it is to think about this game we've defined and compute what is the Nash equilibrium strategy for the learner. Okay, so first let me tell you what is the like existential theorem you get. We'll look at what the algorithm is, then we'll look at some plots. Okay. So first of all, there exists an algorithm parameterized by an arbitrary collection of groups that can take as input any sequence of models and any sequence of nonconformity scores. These models and nonconformity scores can again be arbitrary and so can depend on the past in arbitrary ways. So just to like flag one thing, if you paid attention to like conformal prediction before, in split conformal prediction, there's a need to have like a calibration set that is distinct from the training set that you use to train your model, because you need examples that are like conditionally independent. So if you trained your model on them, you've ruined them. Which sort of cuts your effective sample complexity by some fraction. You need like to pull that set for calibration. We don't need anything like that here, because we're making no assumptions on the sequence of models or nonconformities. You could at every round be retraining your model on all of the examples you've seen so far, and you could be reusing that data. Right. So the models of the nonconformity scores can also change at every round. Against any sequence of examples, which can be chosen by an adaptive adversary, the promise is that with probability 1 minus delta, for every threshold tau and group X that we care to zoom in on, the coverage error on that group, the difference between our target coverage and our empirical coverage, goes to 0 at a rate that's like 1 over the square root of the size of that group, which forever is sort of like the statistically optimal rate. That's what you get if you knew the distribution. Okay, and there's like thus far, everything's non-constructive, but like actually you can like pin down the algorithm. It's some approximate equilibrium of the game we've been talking about. And I don't want to belabor like the details of the algorithm, but I'm flashing it up on here to convince you that it's a simple algorithm. It's nothing complicated is going on. Let me just walk you through the form of the algorithm. At every round, beginning of every round, we see an example X. We see the feature vector. In particular, from this feature vector, we know which groups it is a member of. Okay. So now we're going to compute a number for each threshold that we might predict. That number is the sum over the groups that today's example is a member of. Which groups we are summing over depends on today's example. And we will compute some number that sort of depends on the history of our predictions and mistakes on that group. Okay, and we'll sum these numbers up. That's it. And then we'll see if for all of the thresholds, this number we've computed is positive, in which case we'll predict. Oh, I'm normalizing things that the nonconformity scores are between 0 and 1. We'll predict like the biggest nonconformity score in that case, which gives us the trivial prediction interval, which covers everything. If they're all negative, I'll predict like the trivial prediction interval that covers nothing. And I don't expect either of these to be the case, typically. Typically, some of them are positive and some of them are negative. And if that's true, then there must be some first threshold tau, such that for threshold tau, so the number positive, and for the next threshold up, in some discretization, the number is negative. Right, like if I have both positive and negative ones, then the sign must change at some point. And when that's the case, this is the typical case. Like these would be very unusual. This is the typical case. So almost all of the action is here. When this is the case, I'm going to randomize between these two thresholds at some point. That's it.
Complexity from here to the exponential constant. Let's say what's the difference?
There's a negative here. There's a
Oh,
so basically the coverage loss could be positive or negative. The coverage, maybe I'm over covering on this group, maybe I'm under covering on this group. If I'm over covering on this group, then this is a big number and this is almost 0. If I'm under covering on this group, then this is almost 0. This is a big number. And so depending on which of those two cases it is, this will be a very positive number or a very negative number. This is the positive number when we're over covering, a negative number when we're under.
Aaron,
Yes.
what is the role of epsilon, and especially epsilon didn't appear in the theorem in the previous slide?
Yes, good. So epsilon is some discretization parameter that I'm mostly glossing over, but think about it as something really, really, really small. So let me briefly lift the blanket over what I'm glossing over. So if there was like one like technicality in like this min-max argument, which was that, right, I claimed that if I know the conditional label distribution, if the adversary has told me the label distribution, then I can read off from the CDF a threshold that gets me exactly 95% coverage. Well, that's not actually true if the distribution were a point mass. Right, like if the distribution, has a point mass at one point, then any interval I might read off has either 0% coverage or 100% coverage, right? If it's not a continuous distribution, I'm in trouble. So there's a technical assumption here, which is that the adversary must be predicting a continuous distribution. And it's a quantitative version of that sort of says it shouldn't put too much mass on an interval that's too narrow. Now, as a function of what that parameter is, there's some discretization parameter here, which is this epsilon that you're flagging. Again, for all of this zero-sum game stuff to make sense, we need a discrete action space. So we're talking about not the interval of not the continuum of all possible thresholds, but some discretized at level epsilon. And what that epsilon has to be like basically the less Lipschitz the distribution we're assuming is, the smaller that epsilon has to be. But our algorithm, neither in its bound nor its running time, have any dependence really on epsilon. So think of epsilon as the smallest number you can imagine, like the smallest floating point number representable on your computer or something. It has to be something for like technical reasons, but we'll see, like the epsilon did not appear in the bound. That wasn't because I was hiding it. It was because it really doesn't appear in the bound. It appears in the assumption we need to make. And the assumption is the weakest when epsilon is the smallest, and it doesn't appear in the running time. So think of epsilon as a really tiny number.
Great. Could you go to the previous slide?
Yes.
Could you comment a little bit on the role of the denominator on the right-hand side? Like typically in most of the bounds when we want, we have a square root over n there, where n is the number of samples. So it's sort of very clear that as I have more samples, this bound is better and better. But here the n depends on tau. It also depends on one element of the group. And so the interpretation of it appears very nuanced. So if you could elaborate a little bit more.
Great. So if I made this sound complicated, I did it wrong, because this is the right n, right? Like this quantity, right? The quantity on the left-hand side, it's an average over how many things? NST things. And so if everything was in the distributional setting, if we were predicting correct 95% prediction intervals, I would expect that my empirical miscoverage would differ from my target, 95, by exactly 1 over root the number of things I'm averaging over.
Mhm.
And that's what the thing on the right-hand side is. It's exactly how many things we're averaging over on the left-hand side. That make sense? We simultaneously have promises about different averages, one average for every group and threshold. And what we're saying here is that we get the right empirical miscoverage, right? The right like variance basically, simultaneously for each of these things we're averaging over, where the right thing depends on how many things we're averaging over.
Mm-hmm. Yes, but isn't it the case that this n could actually be small, not necessarily large? Let's say
it is the case that the n
very
could be small. That's right. And so if the n is very small, then your empirical coverage won't be very big, but won't be very good. But neither would it be in the best of cases where I really knew the distribution and was predicting correct 95% prediction intervals. Just because if I'm flipping only 5 coins, then it's not that surprising if I only get one heads. Make sense?
Thank you. Yeah.
Do you assume I can work for any cyclical model and any sequence of score function? So what's the cost for being able to do this?
Well, so we are working in the sequential setting, which does mean that we have to be able to observe. I think so here is, I think, the biggest weakness of all of this, which is the weakness of the sequential setting generally. Like the way we're able to do all of these wonderful things is that we're assuming that after each prediction, we get the true label and get to sort of update our predictions as a function of that. For all of its failings, the batch setting, that we sort of assume the data is IID, for all of its failings, the batch setting allows you to deploy in a setting where labels are not available. Here we need labels. I think that's the biggest weakness of what we're doing here. Yes.
Is it possible for this M to be zero? For example, we have a few groups. Is it possible that the adversary gives you, something that's not mental?
Sure, or. I mean, if there's nobody from the group, then. The guarantee for that group is like value. Our coverage is undefined. The only promise is that it's like less than infinity.
So it's an all.
Yeah. All right, here's the algorithm. I could show you experiments, but it, like 12:59, people have started to leave. I don't exactly know when this seminar is supposed to end, but like, this is the end of the theory part, the rest of it's just like plots and stuff, so up to you all.
Maybe you can wrap up in the packet.
Sure. Let me go through like 5 minutes worth of plots. So this is a very simple algorithm, right? You can run it. We did run it. And so let me show you some maybe example of some demonstrative settings. So the first is going to be an entirely synthetic setting. We're running this against split conformal prediction like on its own turf. Okay, so it's a synthetic linear regression problem. There really is a distribution. The data is drawn IID. Okay. It's a simple distribution. The y is some linear function of the x's plus noise. And we're just gonna, it's a regression problem, so our prediction sets, they're just prediction intervals. And we're gonna compare what we do to split conformal prediction. And what we're gonna find is that even though this is like really the turf of split conformal prediction, right? Like there's no distribution shift, there's no groups, we're just measuring marginal coverage. That we have, when we run this many times, and we look at the histogram of our coverage rate, okay, the target coverage here is 90%. We are more clustered around the target coverage rate than split conformal prediction, and our prediction set widths are systematically lower, which is good. Why? Well, it's because split conformal prediction, in order to maintain exchangeability, has to not train on all of the data. It's got to separate the data into a training set and a calibration set, basically. And we don't have to do that. So both of these things are getting labeled as they arrive and are retraining their models every round. The models are getting more and more accurate as time goes on. But we are getting more accurate faster because we're training our models on all of the data. And split conformal prediction has to train the model on just a fraction of the data. And that's not just a theoretical assumption. We've tried running it when you run split conformal prediction training on all of the data, and it like falls off a cliff. That's like really important. Yeah.
Is there another version of conformal prediction? Not split, it's conformal prediction, where they use all the data, all the.
There is like a sort of leave one out kind of version that we did not try, and my understanding is like quite expensive to run. You basically have to retrain n times every round.
Wow, that was just curious.
That's right. So there is a version that could do that, but we didn't run it. And I've never seen a paper of this.
Yeah, it's good.
Okay. How about group-wise coverage? Okay, another synthetic linear regression experiment. There's 10 binary features that each index a group that you might be a member of or not. Okay, so these are intersecting groups. And again, the linear regression problem, the only thing we're varying is how much, so the expectation of the label is some unknown theta.x. The only thing we're varying is how much noise is added to the label. And if you're in group 0, there's only a little bit of noise. If you're in group 1, there's a lot of noise. The algorithm doesn't know that. So for split conformal prediction, there's sort of two things you could do. You could just ignore the group structure and just come up with a single threshold, or you could separately calibrate on each of the groups. And because people are now a member of multiple groups, you could use the most conservative, right? On each group, you get some threshold. If you're a member of multiple groups, you get multiple thresholds, we'll use the most conservative, which guarantees, the target, which guarantees at least 95% coverage, but might overcover. And what we find indeed is that, when we use split conformal prediction that doesn't know about the groups, then it's, sometimes, on the low noise group, it overcovers. On the high noise group, it undercovers. When we use the conservative thing, it often overcovers, and we hit the correct coverage rate on each of the groups. And similarly, we get, like on the low noise group, hey, we get the correct coverage while getting a much lower prediction set size, which is the correct thing. And in fact, we're lower everywhere except on the high noise group when we correctly get a large prediction set size. You can replicate this on real data. Let's do the same thing on California census data, where the groups are defined by race and binary gender. And although it's less pronounced than our synthetic experiment, you get the same effect, which is that you can get both under and over coverage. If you don't tell split conformal prediction about the groups, you get systematic over coverage if you do, and we get the right thing. Unanticipated distribution shift. So here, initially, the data is still census data. Initially, it's coming from California. Split conformal prediction is calibrated on California data, but then deployed on Pennsylvania data. It didn't know the change was coming. Our algorithm got like a warm start on the California data, and then at some point switched to Pennsylvania data. It didn't know the change was coming. Split conformal prediction due to the distribution shift, systematically overcovered. We get right about the right coverage, and also have a sort of distribution of interval widths that is smaller. And that's it. So thank you. You can guess if these are blueberry muffins or.
Hello, Aaron.
Yes.
Yes. So I had been following the work from Emmanuel that you mentioned earlier, and looking at the history of his papers, I think he did perhaps regression first and then classification. And I think more recently he's gotten into something like object detection in images. And he sort of argued that somehow the way to compute these intervals was a little bit different and harder as you moved from continuous predictions to discrete, and then to these sort of more structured object detection type predictions. Can you comment a little bit on whether your framework is applicable to all problems in the same way, or what are the distinctions depending on the prediction task?
Yeah, so let me answer with some caution, because I'm a relative newcomer to this literature. But my understanding is that a lot of the innovation over the last 5 years, say, extending conformal prediction from, sort of naive regression to maybe more sophisticated quantile regression to classification to other things, has been in the design of the nonconformity score. So oftentimes the wrapper is split conformal prediction. And, when you read a new paper about applying it to like ImageNet predictions, what's going on is they've designed a clever new nonconformity score. And so just as split conformal prediction is like a wrapper procedure that works for any nonconformity score, so does our method. So in our paper, we compare to a bunch of different approaches, and it's always an apples to apples comparison in that we use the same nonconformity score for both sets of experiments, split conformal prediction and ours. Oftentimes, by the way, the main contribution of like the paper we're comparing to is like the nonconformity score. So it's not like we're improving on the contribution of that paper. We're using the contribution of that paper in a different way. But regression, classification, all of these things fit into the framework by the careful choice of nonconformity score.
New tools available.
Yes, all of the code is available on GitHub from the paper. Thank you. All right.
Yeah.